Hello friends. So, one second. So today hello friends. So today we are going to solve 3 questions, and these 3 questions are somewhat, you can say, directly, or we can also say that they are directly related with the projectile. And so the first question, it states that a beach ball is thrown vertically upward from the ground with an initial speed of v naught. The ball experiences a linear air drag force given by F drag, that is minus m beta times v, where beta is a positive constant and v is the velocity of the ball. Determine the speed vf of the ball just before it returns to the ground. Compared to the motion in the vacuum, does the ball spend more time or less time in the air? Justify your answer quantitatively. So in this case, we have to, because the ball will be, you can say, traveling in upward direction, and then it will be returning to the ground. Okay. So therefore, we are going to take that our up is our positive. Okay. So you can say on the way up, we are going to take that our velocity is positive. And as it is going to move in the upward direction, the drag force will be pointing in the downward direction. Okay. You can say our drag force points downward. And when it is on the way down, that will be entirely opposite of that. So you can say on the way down, we are going to take that our velocity is our negative, and the drag force is going to point upward. Drag force points upward. So it means the velocity and the drag force will be always in the opposite direction with respect to their sign as well, specifically sign. And so let us consider the force and the equation of motion. Force and equation of motion. So we can write that the force, you can say that our force both up and down, okay, we can say that our total force, that is our up and down, that is our F, which will be equal to our minus mg and minus of our the drag force, that is our m beta times v. So this is the basic equation of our total force. And from here we can write our acceleration. So the force, we can write this as mass into acceleration. So we can say our mass into acceleration will be equal to minus mg minus beta times v. And here we can cancel out mass throughout. So this gives us that our acceleration is equal to minus g minus of beta times v. And acceleration we can also write as dv by dt. And we can modify, okay, let me write it here. We can write that our acceleration is equal to dv by dt. And we can write this acceleration with respect to the distance also. Suppose the distance is with respect to a y. Okay, the distance it has moved. Okay, so we can write this as our dv by dy multiplied by dy by dt. Okay, this is a basic differentiation. We usually use this property. And this can be written as our dy by dt is nothing but a velocity. So we get our acceleration is equal to v times dv by dy. Okay. And we substitute in the equation of acceleration. We get this as our v dv by dy will be equal to minus g minus beta times v. Okay, and we are going to use the variable separation. Okay, and from here we get that our v divided by g plus beta times v is equal to minus of our dy. Okay. And now we are given two types of motion. One is upward direction and other one is our downward direction. So let us start with our first, that is our upward motion. Upward motion. So we can just draw the approximate figure for that. And suppose this is our y is equal to 0, that is the initial point, and the total distance is traveled is suppose our h. So the topmost point becomes y is equal to our h. And at y is equal to 0, if its velocity is our v naught, then the velocity at the y is equal to h will be obviously equal to 0. Therefore, we can integrate the equation of our this, let us call this equation number 1. So we can say from equation 1, we have the limits of our y is going to vary from 0 to h, and the velocity is going to vary from v naught to 0. Okay, so we are going to simply integrate it, and we get this as velocity varies from v naught to 0, and we have this as v, and this is g plus beta v, and on the this is negative sign, and the height varies from 0 to h, and this comes as our dy. And our integration, so this is quite straightforward. We can take our, let me solve this separately, especially the left one. So this is our beta plus v, and we can take from here that we can write this is 1 upon beta, and this will be 1 minus g upon g plus beta v. This we can easily write. Now we simply integrate it, and so we get the integration, and this will be giving us 1 upon beta, this comes as v minus, and here we have our g natural log of g plus beta v, and this g is divided by our beta. So this is our integration, and we are supposed to put the limits, and limits is from v naught to 0. Okay, so limits are from v naught to 0, and on the our right side we are going to get this as minus of h. So this is equal to over minus of h. Okay. And if we substitute the limits, we can just straightforward write it as our minus of h is equal to, and this will be over 1 upon beta, upper limit of v is 0, so this comes as a 0 minus g upon beta natural log of our g, minus, and the lower limit is our v naught, so this comes as v naught minus g upon beta natural log of g plus beta times v naught. So finally we get this as our h will be equal to, and if we multiply, this will be our minus minus plus, so this comes as v naught upon beta minus, we have this as g upon beta square, and natural log of this will be coming as positive, and this will be over negative, so we can write this as g plus beta naught divided by g. So this is our height when it is moving in upward direction. Okay. And next is our downward direction. Okay, same thing, but now the integration is going to, or limits are going to change from integration. So we can say next is our downward motion. And same diagram we can draw. So for the downward motion, once again it is going to start from y is equal to h, and it is going to end at y is equal to 0. Okay. And at y is equal to h, its velocity, because it is going to start from rest, will be equal to 0, and the velocity at y is equal to 0 will be our minus of vf. Okay. So same equation, that is equation number 1. So we can say our equation number 1, that was our v dv divided by g plus beta v and minus of our dy, and we simply put the integration limit. It goes from 0 to minus vf, and on our right side it is going to go from h to 0, and same value, but limits are going to change the ultimately what we are going to answer. So I'm straightforward going to write the value of h. Okay, so we are going to get that our h is equal to, only the sign will be our negative, so this comes as vf upon beta, this comes as minus g upon beta square natural log of 1 minus, and this comes as our 1 second, yeah, it is plus, it is 1 minus beta v naught by, and this will be going as beta vf upon g, and this suppose is equation number 2, and this is our equation number 3, and here height is when the moving downward direction. So both equation 2 and 3 are the representation of the height, so we can simply equate them. So you can say from equation 2 and 3, 2 and 3, we are going to equate them. So we get this as our V naught beta minus G upon beta square natural log of 1 plus beta V naught by G is equal to, now with a negative sign, so this becomes minus Vf upon beta minus G beta square natural log of 1 minus beta Vf upon G. And we can just sort out this beta term. So this goes by beta here also and here also. Okay. And we can just combine our velocity terms on one side. So we get this as our V naught plus Vf is equal to, and on the right side, this will be giving us a positive sign. So this is a negative sign. So we can write this as G upon beta natural log of, we get this as 1 plus beta V naught divided by 1 sorry, I missed out G. So this is G and 1 minus beta Vf upon G. Okay. So this is our velocity relationship. Okay. And this equation can be used to determine the value of our Vf if all the rest of the values are known to us. Next we come to our we can say we need to find out the time also. Okay, so we are going to once again start with the motion equation, and we know that our equation of motion, and this equation of motion we know that we have written as F is equal to minus mg, and we have this as minus m beta times v. And our force is nothing but mass into acceleration. So we can write this as mass acceleration, we can put straightforward dv by dt is equal to minus mg minus m beta times v. Once again this mass goes away, and we get that our dv by dt is equal to minus g minus beta times v. Okay. And now we are going to once again do variable separation, but this time with respect to time t, because we have to find out the t. Therefore we can write that dt will be equal to minus, and this comes as our dv and g plus beta times v. Okay. Once again, let us call this equation number, this will be equation number 4. Now upward motion and downward motion. Okay, same thing, but now with respect to time t. So we can say our time for upward motion, let us suppose that time is t1. Okay, and now we have to define the limits. Okay. So now we are going to discuss same thing but with respect to our time. Okay. So at launch the time is our 0, and when it reaches the top the time is equal to our capital T1. At launch the velocity was our v naught, and at the top the velocity is equal to 0. Okay. Same things but with respect to their time, and therefore we can write that using equation 4, we can say that our integration 0 to t1 dt is equal to minus, and this comes as a v naught 0, and this is our dv g plus beta times v. Okay. And this is quite simple integration, straightforward. I'm going to write the value of t1 because right side we have already evaluated. Okay. So there won't be much of the difference. Only difference is that when we evaluated our h, there was v in the numerator. Okay. So this is the only difference. Rest of the equation is our same. Therefore, we can say that our T1 is equal to, this will be coming as 1 upon beta natural log of 1 plus beta v naught upon g. So this is the time in the upward motion. Similarly, we are going to find out time in the downward motion. So you can say time for downward motion. Okay. And for this same process we are going to use, so it is going to start from the top, and our top, let us suppose the time downward motion is our T2. Okay. So we can say that it is going to start from time T2, sorry, not time T2 but time 0, and it is going to reach here at time T2, and initial velocity will be 0, and here the velocity will be equal to minus of Vf. So straightforward, once again using equation 4, we can write that our dt is going to vary from 0 to T2, a is equal to minus, and this comes as 0 minus of Vf, and this is our dv, and we have g plus beta times v. And only difference will be of a sign. Here it is positive. In this particular case, we are going to get negative, and along with here also. Okay, this is the minor change. So we can say that our T2 will be equal to minus 1 upon beta natural log of 1 minus beta Vf divided by g. So this is the time taken in the downward direction. Okay. Now total time we can add T1 and T2. You can say total time, let us suppose that is about T, which will be equal to T1 plus T2, and we substitute them, and we get this as T is equal to 1 upon beta, we can take as common, so we get this as our natural log of 1 plus beta v naught upon g minus, and this comes as natural log of 1 minus beta Vf upon g. Okay. And using the logarithmic property, we can combine these two. So we get T is equal to 1 upon beta natural log of, we can write this as g plus, rather let's take the LCM, g plus v naught and g minus vbf. Okay. So this is our total time taken. Okay. And obviously we have to make a comparison with respect to vacuum, and vacuum there will be no drag. Okay, so the time taken in upward direction as well as in downward direction will be same. Okay. And there will be, therefore we can say that in vacuum, let us call the total time taken is T vacuum will be equal to, this will be twice v naught upon g, downward and upward total. Okay. And for our this total time T, and we can say with air drag, we can write our time T is equal to our v naught plus Vf upon g. And we know that the velocity in the air drag, that is Vf, will be obviously less than the velocity in the vacuum. Okay, that is basic. So we can say that our Vf is less than our V naught. So we are going to divide both sides by G, and further not we are going to add V naught by G and to both sides. So our left becomes our V naught plus Vf upon G is less than twice V naught upon G. Okay. So which basically means that our time taken in our air is less than time taken in the vacuum. So it means ball spends less time in air than it would be in vacuum. That's a basic conclusion here. Okay. Now let's come to the second question. And in the second question, it states that a particle of mass m moves freely on a horizontal frictionless plane. It is attached to one end of light inextensible string that is partially wrapped around a fixed frictionless vertical pole of radius r. See the top view. Figure I'll draw later on. You hold the free end of the string and can pull on it while moving your hand around the pole. At a time t is equal to 0, the particle has a velocity v naught, moves tangentially along a circular path of radius capital R as indicated by dotted circle in the figure. You are required to pull the string in such a way that the particle continues to move along the same circular path of radius R and the string remains continuously in contact with the pole at all times. Determine the speed Vt of the particle as a function of time. So this question, if you read the statement, it looks very complicated, but once I draw the figure, you will clearly understand that is much more easier as compared to the question, the things which I've mentioned in it. So, and the pole we are looking from the top, and it says that we have, this is our pole, and there is a dotted outside the pole, and the radius, suppose this is our center, so this radius is our small r, and the radius of this dotted is given as capital R. Okay, and here it is mentioned in the question that there is a string. To the one end of the string, a mass is connected, and that string is wrapped around the pole such that it acts as just you can say like a tangent. Okay, it's not wrapped but just touching the pole, and it is something like this. Okay, so this one end is our mass, other end is our hand. Okay, and we are going to, you can say, move this hand in this direction. So obviously the mass is going to move in opposite direction, but there is a condition that this string should be always in contact with the pole. Okay, this condition has to be satisfied. Okay, so this is important part here. Okay, so in the question, it is very lengthy question, but the end, so you can say the basic figure is we have a pole, and remember this is top view. Okay, from the top we are looking at it. So the inner is our pole, which is radius r, and the mass is moving in a radius that is our capital R, and there is a string which on the one end we have a mass connected and other one is our hand, and this string is always in contact with this pole. This is the basic question, and we have to find out the speed. Okay. And so we can say that we are having the mass moves in a circle of radius capital R, mass moves in the radius of capital R, and we are also given that the string is tangent to the pole of radius r. So we are given that our string is tangent to pole of radius small r. Okay, and so let us redraw this circle, and we are going to draw some of the forces and also identify the angle. Okay, angle we are going to. So we have our inner pole, and we are having a circle of capital R. So the mass is one extreme end, and the string is acting as a tangent. And if ever this is, suppose this point is our A, this point is our B, and center we are calling it C. So therefore we can say that this R will be perpendicular to the tangent. And if we join this A to C, so this AC will be our capital R. Now this in triangle our ABC, we can write that in triangle ABC, we can say, let us suppose this angle is our theta. So we can say that our sine of theta will be equal to small r upon capital R. Okay, so it means our this theta angle is only dependent upon the radius of the pole and the radius in which this mass is moving. Okay, so it means this theta will be constant all the times, because our radius in which mass is moving is fixed, as well as our radius of the pole is fixed. And if we define, let us suppose the string is having a tension, and let us store that tension as our F. And this F we can divide into two components. One will be our tangential component, and other one will be our radial component. So let us suppose this is our tangential component, and this is our radial component, and AC is given to us as capital R. So there are two forces. So we can say forces on the mass, forces on the mass. Okay, and we assumed that the string tension let us suppose is represented as F. So we can divide this F into two components. First one we can say is radial, and second component we can say is our tangential. So these are the two components, and the radial component is our for you can say provide centripetal acceleration, and the tangential component will be used for our changing the speed. And let's write now our radial equation. You can say that our radial equation, and let us write the centripetal acceleration or radial acceleration is our a of r, which will be equal to our v square upon capital R. And also we can write that our radial force, okay, so this our radial force is our, let me draw it here, so this is our A, B, and this is our force F, angle theta. So we can divide this into two components. We get this as F cos of theta, and this will be F sine of theta. So F sine of theta will be our tangential, and F cos of theta will be our radial. Therefore, we can say that our radial force which is our F cos of theta will be our mv square upon r. And similarly, we can write for this was our radial, and same we can write for our tangential. Tangential equation, and our tangential acceleration, we can write this as a first derivative of our velocity, and our tangential force we can write this as F sine of theta, and that will be our tangential acceleration, that is our first derivative of our velocity. Now we have two equations. Let us call this equation number 1 and equation number 2. We are simply going to eliminate our force. Okay, so simply divide them. So we can say equation first and second, we can write F sine of theta, F cos of theta will be equal to our m first derivative of velocity, and we have mv square upon r. So here force goes away, therefore we can write that our tangent of theta will be equal to mass also cancels out, so we get this as our r velocity first derivative divided by v square. Okay. And from here we can say that our velocity first derivative will be equal to v square upon r tangent of theta. Okay. Now we can you can say solve for our velocity, because we have to find out the velocity at time t. Okay. Therefore, we can remodify or rewrite this equation as our dv by v square is equal to 1 upon r tangent of theta and derivative with respect to time t. And we have to put the limits. Okay. So we are given that initially its velocity v naught, and at certain time the velocity is given v. Okay. Let me write it here. So you can say that our time t is equal to 0, our velocity is our v naught, and a certain time t the velocity is our v. Okay. So on the right side we are going to get this as 0 to t, and this integration is quite simple, so we can just write the result. So we are going to get this as 1 upon v naught minus 1 upon v is equal to tangent of theta divided by r multiplied by t. We are interested in this value v, which is basically a time dependent, so we can remodify this as our v of t will be equal to, and we can write this as 1 upon v naught minus tangent of theta upon r times t, and we can write this as minus of 1. Okay. And think this was the only thing that was asked for. Determine the Vt as a function of time. Okay, that was only the thing that was asked for. Okay. And so this completes our second question, and then we come to our third question. And the third question, it states that a uniform chain of total length L lies on a smooth frictionless horizontal table. One end of the chain passes through a small hole in the table with the initial length y0 hanging vertically below the table. The chain is released from rest. Determine the length y of t, that's a chain length as a function of time, of the chain hanging below the table as a function of time up to the instant when the chain completely loses contact with the table. Find the speed of the chain at the moment it just leaves the table. Neglect the air resistance, assume that the chain remains taut as it moves. So this question, you can say, have been asked in this IIT-JEE examination many times, but in a different way. Okay. And basic method we usually know by how to solve this. We are going to use the mass m, or we can say it's linear mass density lambda, and based on this we are going to solve that. Okay. But here it is little bit you can say remodified. We have to find out the speed as it is going to just leave the table. This is our second part, and first part is we have to find out the length, that is y, as a function of time, basically the equation. Okay. This is the basic two parts are there. So let us write what are the things given to us. So first thing that is given as chain length. Chain length is given to us our L, and let us assume that the linear mass density is our lambda. Linear mass density is our lambda. Okay. And it is given that initially y0 is the hanging length of the chain. Okay. So we can write that initial hanging length is our y0. Okay. So this is our initial hanging length. Okay. So we have to remember this. And okay, so let me draw an approximate figure. It is given in the question that there is some kind of hole, but we can draw it with respect to the edge of the table also, that doesn't matter. So let us suppose this is our table, and the chain is hanging initially like this. Okay, so let us suppose this is our chain, and initially it is given that the length that is hanging is our y0. This is given to us. Okay. And so we have our linear mass density, and therefore we can say that the total mass of the chain, so we can write total mass of the chain let us suppose that is our capital M, which will be equal to linear mass density multiplied by the length, that is our L. Okay, and L is the total length. This is our given to us our L. But we are only interested in the hanging part. Okay, and therefore we can say that the mass hanging below the table, mass hanging below the table at time t. At time t. And at time t, let us suppose that is our y. Okay, we have to remember that this y naught is our initial length that was hanging. At a certain time, we can say that the length is our increased. Okay, so let me redraw this figure. For any time t, let us assume that our length that is hanging is our y. This is our length hanging at any time t. Therefore, we can say that mass hanging below the table at time t for length y, and this mass, let us call this as mass hang, will be equal to our lambda times y. And so the only force that will be acting is the force that will be acting in a downward direction. Okay, therefore we can say that our force causing the motion let us suppose that force is our F, and that force F will be equal to mass hanging multiplied by G, and mass hanging we know, therefore we can write that the force will be equal to our lambda y times G. Now we can use Newton's second law. This force is going to produce an acceleration. Therefore we can write that our but we have to remember this entire chain is going to accelerate. Okay, it won't happen that only the small portion is going to accelerate. So we can say that our entire chain accelerates. And let us suppose it accelerates by acceleration of over a. Okay, and the total mass we know is our lambda times L. Therefore we can say that our F is equal to mass into acceleration a, and we can write this as our lambda y times G is equal to mass we know our lambda L and times a, and a we can write with respect to our y double derivative. Okay, and here this lambda cancels out, therefore we can write the equation of the motion that gives us that y double derivative is equal to G upon L times y. So this is basically our equation of our motion. Equation of motion. Okay, and now we can reformulate this double derivative of y in terms of our velocity. So we can write this will be equal to we can write double derivative is equal to v, and this comes as a dv by dy. Okay, and this will be equal to over gl times y. Okay, so we are going to simply separate the variables. So we get this as v dv is equal to, this comes as our g upon l, and we have y times dy. Okay, now we are going to integrate. So let's write the limits of integration. So we are already given in the question that initially the length of this hanging chain is our y naught, okay, and initially it is at rest, so velocity is equal to 0. So this is our initial condition, and final condition we can assume that our y is at a certain length of y and its speed is our v. This is our final condition. Therefore we can integrate that our velocity goes from 0 to v dv, and this we have our g upon L, and integration goes from of our y goes from our y0 to y0 to y, and this comes as y dy, and this is a quite simple integration. So on the left side we get v square, so you can write this as v square, and this is our g upon L, and on the right side we are going to get y square, and upper limit is our y, lower is our y0, so we can get this as y square minus y0 square. And for the sake of simplicity, let us assume that this g upon L is our alpha, okay, because so we can write that our v square is equal to our alpha, and we have y square minus y0 square, and this is our equation of our velocity. And we can find out our this we are supposed to find out this y, so we can write our velocity in terms of our dy by our dt. There, one second, sorry, my mistake. Here I'm going to assume, because otherwise it will be giving me square root, so I'm going to say that alpha is equal to square root of g upon L. Okay. Then I can say that my v will be equal to this. Okay. Otherwise it will be giving me a square root. So we can write that our dy by dt will be equal to alpha, and we have this as y square y0 square, and this is square root of this. Now we can use our variable separable. Okay. So we get this as our dy, and we have this as y square minus y0 square is equal to alpha times dt. Okay. Now it is quite simple. We already know our integration limits. So on the left side it is going to start from initial is our y0, final we can take as y dependent upon t, and at time t is equal to 0 and time at certain value of t. And we can, okay, so this integration is quite standard one, and we know that this integration gives us cos hyperbolic inverse. Okay. We can use the standard formula, that is our integration, and this is our dy upon y square minus a square is equal to, we get this as our cos hyperbolic inverse of y upon a. This is our basic integral formula. Okay, and we simply substitute it. Okay, so we get this as y upon y0, and the limits are almost same, so there is nothing much to change. So we are going to get this as cos hyperbolic inverse, and upper limit is our y of t, lower limit is same, that is our y0 is equal to alpha times t. And we can simply say, we can write this as our y of t is equal to our y0 cos hyperbolic alpha times t. Okay. So this is our equation for our, you can say, the hanging length while the chain is still on the table. Okay, we have to remember that this is the hanging length while chain is still on the table. Okay. And we have to find out in part B, we have to find out that the speed when the chain leaves the table. That's our part B. So in the part B, we have to find out speed when chain leaves the table. Leaves the table. And the total length is of L. Okay. So the chain will leave the table when y becomes equal to L. So we have taken this y as any general length, and the total length of this chain is our L. Okay. So when y becomes equal to L, the entire chain will be off the table. Okay, off the table means from the horizontal part of the table. Therefore, we can say that our chain just loses contact with the table when our length which we have taken y becomes equal to our L. Therefore, we are going to use our velocity equation. Let us call this as our, okay, let me write it again. So we have our velocity equation, that is our v square is equal to our alpha square y square minus y naught square. Okay. So in this equation we are going to put y is equal to our L. So we can say that velocity at which it is going to leave will be equal to alpha, and this comes as L square minus y naught square and its square root. And alpha we can again put back. Okay, so alpha was our square root of GL, so this comes as G upon L square minus y naught square and its square root. So this is our velocity at which it is going to leave the table. And in normal, you can say sometimes this question is because we know that when the normal, or we can say the normal force, when it becomes equal to 0, then also we can solve it by using that the normal force on the table, it becomes equal to 0. Okay, so it means suppose this is the portion of the chain on the table. So here it is going to have some normal force, and when this normal force becomes equal to 0, the chain is entirely off the table from the horizontal portion. So sometimes some of the books or some of the solution can be provided by using this method also. Okay. But both the methods are going to work. It's not a big problem. Okay. But here we were interested in the velocity part, and sometimes along with this normal, they also use the concept of potential energy as well as the combination with our, or we can say the energy conservation. So that also we can use to find out this velocity when the chain is entirely off the table. Okay. So this completes all the 3 questions for today. Thank you.